Okay, so we can start today's lecture, and we were dealing with this expectation of the random variable. Okay, expectation of this random variable we are dealing with, and we have seen that if we flip two coins simultaneously, then in an expectation or on an expectation, I'll be getting one hit. Okay, that we have analyzed. That we have analyzed in the last class. Okay. In the subsequent lectures, which will be very much necessary, is that we'll be looking for the expected number of heads in one coin flip. One coin flip. If I am flipping one coin, okay, what is the expected number of heads? Even if it is not realistic, okay, the result, but that result cumulatively will be giving some kind of big picture, okay. So this expectation of x for the expected number of heads in one coin flip. If I flip one coin, okay, right. So in that case, we know the sample space is head and tail. If I flip one coin, one coin, okay. So that is the sample space, and I'm looking for number of heads. So the random variable here, I am denoting number of heads by x. Then if I flip one coin, then what will be the value of x? Can you tell me? Hmm? 0. So 0 means tail has come out. And 1 means head has come out. Okay. So the random variable can take two values, 0 and 1. Okay. Now if we transfer this into this formula, this knowledge into this formula, that expectation of x formula, then what we are getting? X times probability x equal to x. So that will be 0 times probability x equal to 0, 1 times its value 1 times probability x equal to 1. So 0 times whatever is 0, and then 1 times probability x equal to 1. What is probability x equal to 1? Whenever I am flipping one coin, half. Okay. So this half is coming over here. 1 times half, so this is half. So there is no practical significance. If I flip one coin, what is the meaning of half coin? Okay, right? But if I cumulatively, that's the final remark is whenever we will be flipping, say, 100 coins, 100 coins, or n number of coins, n could be 100, n could be 10,000, whatever. Then we'll be seeing some kind of meaningful inference out of it. That is exactly the next couple of hours talk will be based on this. Okay, so this thing, expectation of x in accumulation, what it is giving. Okay, and that is the big picture that algorithmic analysis in randomized parlance. Okay, taking in an ad hoc basis every now and then. Okay, right. So let us look into that scenario when this thing in accumulation is coming into picture. Okay. So the term which is related to this will be coming linearity of expectation. Very important term, linearity of expectation. And next, after a couple of minutes, another term will be coming that is called indicator random variable. Okay. So these two in combination will be taking the help of this idea, and will be giving very good result with an ease. Okay. So that is very much important. Okay. So this is a great tool for analyzing the linearity of expectation and analyzing randomized algorithms. And here we'll be representing the essential point with an example. What is this linearity of expectation? Without going into too much mathematical detail, okay, that means proof and all this, we'll be trying to understand mathematically obviously, but little bit in a more lucid manner so that you can grab the essential point. Okay. So here what we will do in this linearity of expectation, or what the linearity of expectation will be doing, is that we will express a complex random variable in terms of summation of simpler random variables. And then we will find the expected value of that complex random variable by applying the concept of linearity of expectation. Okay. So here the main idea is a big complex random variable. We have to decompose it into simpler random variables. And that simpler random variable in isolation we have to analyze, and that is easy. And then we will be summing it up. So the first example that is coming into our mind is again these flipping coins. Okay. So this flipping, we have to observe that flipping two coins simultaneously, okay, is equivalent to the fact that flipping two coins in a sequential manner. Okay. So two coins we are flipping simultaneously, right? And then if I flip it one after another, first I am flipping one coin and then I am flipping another coin, okay? And then I can see it as a big experiment, and then the same sample space will become HH, HT, TH, TT. Okay. So these two coin flips simultaneously, and then I can write its sample space HH, HT, TH, and TT. It will be even more complex whenever we will be having three coins simultaneously. I am flipping three coins, okay? Then the sample space will be HHH maybe. Then HHT and so on. Okay. If I am having 10 coins, I am flipping simultaneously. So the first outcome, elementary outcome, will be 10H. 5, 6, 7, 8, 9, 10. So even means this page will not be sufficient to put all this. Okay. So this is a big experiment. I am thinking all n coins or all 10 coins I am simultaneously flipping, and then the outcome as a big picture I am taking, as a big experiment I am taking the outcome, and then I am jotting it down. Okay. And I am noting it down, right? Then the life will not be easier. Okay. But if I see that the 10 coin flips in a simultaneous fashion is equivalent to the fact that I am flipping one coin at a time sequentially 10 number of times. Okay, the first coin I am flipping, then second coin, then third coin. Okay, and each of the coin flip separately I am trying to analyze. So each of the coin flip, I know that is a single coin flip experiment. Okay, each coin, with the first coin I am flipping and it's whatever sample space is created out of that. I am noting it down. That means that is a single coin flip. So the sample space is H and T. The second coin flip in isolation I am taking. Then again the sample space will be H and T for that. The third coin flip in isolation I am checking. Okay, right. And whatever we are trying to show here is that if I am taking two coin flips simultaneously, the expected number of heads, whatever result I am getting, that will be equal to the case if I am treating each coin flip separately and I am calculating how many number of heads coming in two coin flips. Okay. Then you will be seeing that it is very easy in the latter case whenever I am taking it sequentially, right? So with an example we are trying to understand this fact that what is the essential point of linearity of expectation. So here what we are doing, we denote the number of heads in the first coin flip by x1, this random variable. Okay, I am taking each coin flip separately in isolation. And the number of heads in the second coin flip by x2. Then the number of heads in two coin flip will be denoted by x and could be represented by x equal to x1 plus x2. So this is the random variable for the first coin flip, how many heads, and this is random variable that is counting for the second coin flip, how many heads. Okay. And if I add these two, that will be giving the number of coin flips we are having, number of heads we are having for two coin flips. Okay. Now, if I take the expectation both sides, expectation of x and then expectation of this x1 plus x2, I am taking expectation both sides. Just like we multiply some number both sides. Okay. Expectation both sides. And then if what I can get is it is equivalent to this expectation of x1 plus expectation of x2. So expectation of x1 plus x2 we can write in this fashion. Expectation of x1 plus expectation of x2. So let us take what is the value coming out of this. So this expectation of x. Now already we have seen this. Expected number of heads in two coin flips. Whenever I am taking that as a big experiment, simultaneous experiment, then expectation of x in two coin flips. In two coin flips, I have seen that that is 1. Okay. That result already I have got. Two simultaneous coin flip, the expected number of heads. Now this expectation of x we have got, it is expectation of x1, the expectation of, in isolation I am checking each individual coin flip and I am taking its expectation. So expectation of x1 plus expectation of x2. And what we have found in each individual coin flip, in isolation if I am checking, what is the expected number of heads? That is few slides back we have got. Okay, so this is the result. This is the result, and this result we are utilizing here. Okay, so this is half plus half, that is 1. Okay, so you see this expectation of x, if I am taking each individual coin flip as a separate experiment, and its expectation if I am adding up, then I am getting the same answer as we got here whenever I am taking it simultaneously. So a big complex random variable that was in simultaneous case, that we are decomposing it into simpler random variables. And then all those random variables, its expectation I am adding up, and we are getting the same result. Okay. So that is the sole point that we have to make here. Okay. And we are making here that is the point. Okay. So in general, what we can write, if x is a summation of all these simpler random variable, okay, then the linearity of expectation is telling that, okay, the expectation of x is equal to expectation of this xn, and then we have to write like this: expectation of x1 plus up to expectation of xn, expectation of x1 plus expectation of x2 plus up to expectation of xn. So this is the result that we call this linearity of expectation. Okay. And the thing is that here this x1 plus xn, in our subsequent development, this xn I am writing as, or whatever, x I am writing as x1 plus x2 plus x plus up to xn. What I will be writing in our subsequent development, that this is nothing but summation of xi over all I equals to 1 to n. Okay. This series, if I expand, then I will be getting this x1 plus x2 up to xn. So instead of writing this, I'll be writing this. Then our life will be much more easier. Okay. We'll see with an example how it is becoming easier. Okay. And then what we'll be taking the expectation of x both sides. And then expectation of this summation I equals to 1 to n xi. And then by this formula, expectation of x1 plus expectation of x2 plus up to expectation of xn, what we can write? We can take this expectation inside the summation I equals to 1 to n expectation of xi. So if I expand this, then it will be coming I equals to 1, it is expectation of x1, plus I equals to 2, it is expectation of x2. This result is coming. Okay. So by linearity of, what we say is that by linearity of expectation, we take expectation inside because we know this result. Okay. Are you getting? You getting? What am I telling? You. Are you getting anything? Huh? Expectation means what? Are you following the lecture? Are you following the lecture? Huh? What we are trying to find out? With this expectation, what we are trying to find out? Linear properties. Huh? Are you studying in the class? In the hostel? After going back, what are you doing? Last bench, are you getting? No, no, no. Are you getting? What am I telling? Huh? What is that? the expectation will be doing in coin flip experiment? Huh? Average time complexity. Okay, sit down. Are you getting? You getting? What for what we are finding expectation? For coin flip experiment, what we are actually trying to have? Okay. Okay, sit down. What is your roll number? 182. Okay, so maybe with half of the class following, half of the class not following. Half of the class following, half of the class not following. Half of the class is head, half of the class is tail. So I can expect that with probability half, you will be following, with probability half, you will not be following. If each individual guy I am taking into consideration, okay, then it is uncertain, okay, the experiment. Okay. So with that, uh, this thing, this thing will be coming heavily in our subsequent development. This notation will be using, okay, and then we'll be taking this expectation inside, okay, and then this expectation of xi, that means ith coin flip experiment. That means a single coin flip I am taking in isolation. So this is for single coin flip experiment case. The same thing will be happening for hiring assistant problem. This xi will be denoting the ith interview, the ith guy being interviewed. The ith guy being interviewed and whether he or she will be selected or not. So each individual guy, that interview in the ith iteration, one guy will be interviewed. So this xi at that time will be denoting that thing. So that means we are having n number of guys being interviewed. We can take it as a big experiment and we can analyze. But what we'll be doing is, we'll be taking in isolation one guy, just like the coin flip experiment. Okay. The coin flip experiment is going on and the ith interview is going on. So there's a similar experiment. Little bit of probability difference will be there. We'll see it. Okay. But the philosophy is exactly like the same. Okay. So that's why all pain we are taking right now, so that we can fit our coin flip experiment case into our hiring assistant problem. Okay. So we are learning in a probabilistic textbook fashion right now what is expectation, coin flip, and then we'll be channelizing that knowledge into our computer science domain. Okay. That is our objective right now. Next another thing that is out of the class. Next another thing which is very important is this indicator random variable that I was talking about, indicator random variable. Okay. And in CLRS textbook, almost all randomized algorithms they have discussed, they have analyzed using this concept, indicator random variable. Okay, right. So many randomized algorithm can be analyzed with the concept of indicator random variable, which is very important to note. And this indicator random variable provides a convenient method for computing the expectation of a complex random variable in terms of the summation of smaller random variables. So that linearity of expectation, that concept will be coming in this to develop the theory about this indicator random variable. Okay. So that the smaller random variables we can sum up and we can get a big result about the problem we are discussing. Okay. Now let us define this indicator random variable. Suppose we are given a sample species, just like coin flip experiment is equal to say one coin flip, it is H and T, or two coin flips, it is HT, TT, whatever. So we are given a sample species and an event A. We are looking for an event A occurring or not. Okay. So this is the idea. One event I am taking and I am looking for whether that event is occurring or not. It's the binary case, whether that event will occur or not occur. And this simple idea will be helping us to analyze many different things. Because you see, the coin flip experiment, each coin flip experiment in isolation, if I am seeing, then what I am looking for, whether head occurring or not. If each ith interview in the hiring assistant problem, I am looking for, then I am asking the question whether that guy is hired or not. So you see this simple, it is occurring or not. This thing will be coming time and again whenever we will be analyzing randomized algorithms. Okay. So given a sample species, whether one event is occurring or not, that is a big picture. That will be giving a big picture. Okay. So let us define this. So this indicator random variable associated with this event A, that is IA equal to 1 if A occurs, 0 otherwise. 0 otherwise. So this is the definition. It is occurring means we are counting it is occurring 1. It is not occurring, then we are counting it is not. Okay. And computer science is nothing but this analysis or whatever problem we are encountering. Computer science is nothing but counting problem. Okay. In mathematics we are having a big field called counting theory. Okay. All these permutation combinations coming into picture there. And one mathematician or a guy who is trying to become a mathematician, he or she can spend whole lot of 50 years in this one field only, counting. There's a lots of amazing problems are there. And if I see mathematics in terms of counting problem, then a mathematics guy can see, visualize computer science in a much better way than we are. It's nothing but a counting problem. Okay. So that is what we got to understand, what the computer science is. Always what we are doing actually. We are doing in some form some counting. Okay. Okay. Now what we are interested here in finding, we will be channelizing this knowledge into that coin flip experiment again, and then we'll be transferring our knowledge into that analyzing hiring assistant problem. Okay. So when we flip a fair coin, how we can define this sample space and the probability that we already know is equal to this h comma t. One flip we are having, and the probability of h is half, probability of t is half. Okay, that we know. Now, how can we define indicator random variable x associated with the coin coming up heads with this event? How we can associate this random variable x? Okay, so we are associating this x is counting number of heads in one single coin flip, mind you. Okay, and this x is associated with this indicator random variable, which is associated with this event A. Okay, and that we know that that event A is nothing but we are looking for here H. Okay, so instead of A we can write H over here, and that is 1 if H occurs, 0 otherwise. Okay, and now what we can do is, so this is X. You can, if this notation is little bit cumbersome for you, you can omit this notation. You can carry on with this X, but you visualize that X is the random variable which is associated with that event. Okay, and in many cases even we forget this about that indicator random variable associated with that event A, we can we can get that okay, this x is 1 if h occurs, is 0 otherwise. Okay, this is in probability theory, this is called Bernoulli trials as well. Okay, so Bernoulli trials and this indicator random variable is little bit more general, we can say. But all that detailing is not necessary right now. But this is x is the random variable as usual we define, and this is the random variable, indicator random variable associated with this event. If that event A may be H, maybe you are looking for tail also. Okay, at that time it will be tail, whatever. Okay, so here we are looking for H, and for that single coin flip it is 1 or 0. If on that coin flip the head is coming up, I am counting 1, otherwise I am counting 0. Okay, so why I am looking for this counting, because I am trying to find out for n number of coin flips how many number of heads going to come up. Okay, so that is the basic idea. And now sorry, so this x or this indicator random variable IH is a random variable. Okay, mind you. So this x can take value 1, random variable, or can value 0, take some value 0. Now if I try to find out the expectation of this x, then we are trying to find out expectation of this indicator random variable. So then with the definition of expectation, this is x times overall x. We are having probability x equal to x. Okay. Already we have seen this. So this is 1 times probability H and 0 times probability T. So if it is happening, it is H. If it is not happening, it is T. So if it is happening, the random variable value will be 1. So this will be 1 at that time. And what is the probability of that 1? So that will be probability of H. So what we can say here is you see 0 times probability of T and then 1 times probability H. I can put the value that this is half probability H, but that is not our uh, not our objective. Our objective is to show that this probability of expectation of this indicator random variable is nothing but the probability of that event happening. So that event probability H in coin flip experiment, that event might be that ith candidate is hired or not. Okay. So we are getting this big result that expectation of expectation of X indicator random variable is nothing but probability of that event occurring. That event occurring. So this probability, this this probability of this event A. So in our coin flip experiment, this is H. So we can denote that probability expectation of X is nothing but probability of that event A occurring, and it will be different from application to application. Coin flip experiment, it is the head in ith candidate, whether it is hired or not. In that case, it will be the event A. So expectation of X, we can write expectation of X is probability of that event A occurring. And this is our lemma that we'll be using, lemma 1, that we'll be using on and on in an ad hoc fashion several times. And that is given here in this lemma. Given a sample space S and an event A, in the sample space, let X be the indicator random variable associated with this event, then probability, then expectation of X is nothing but probability of that event A occurring. So with that definition, we are proving that. Okay, that already we have done. So this lemma will be using subsequently in our future development. So in the next class, we'll be analyzing this hiring assistant problem with all this knowledge.